The next topic is chapter 5.1.2 wave types. By the end of this section, you should be able to explain the difference between longitudinal and transverse waves. In the O-level class also, the IGCSE class also, you would have learned about longitudinal waves and transverse waves. So here also we will see them, but we will see them in a little more detail than what you learned in the O-level class. Describe longitudinal waves, particularly in terms of pressure, variation, and the displacement of molecules. When it comes to longitudinal waves, you would have learned even in the O-level or IGCSE classes that sound wave is a longitudinal wave. So let me just show this to you. Now see, this is a speaker. It moves forwards, backwards, producing sound waves. So what happens in the case of sound waves? We have air molecules which are moving forwards, backwards. Where the air molecules are close together is where we have the rarefactions. See, I think this is much easier to understand. These dots you see here are the air molecules. Normally, if there is no sound in there, the air molecules will be like this, undisturbed, evenly spread out. But when there is a sound wave traveling, you will see that some areas are having more air molecules, greater concentration of air molecules. Like for example, you see here, and here, because the air molecules are brought closer together. That's why we call it a compression. From the name itself, you can understand where the molecules are closer together, we have a compression. Where they are far apart, we call those areas rarefactions. So this is a compression, this is a compression, this is a compression, this is a compression, and in between them you have air molecules that are spread out. Like for example, here, and here are areas where the air molecules are spread out. We call those areas rarefactions. Even here you can see compressions where the air molecules are close together, it's shown in dark blue, and rarefactions where the air molecules are far apart. We have a vibrating cone. This will produce sound, which will produce compressions and rarefactions in the air. This is the direction of the wave. Okay, let's go back. Describe transverse waves. So, seismic waves, we will see them later. Here we have seismic S and seismic P, seismic S and seismic P. This is S shape. So this, you can remember, this is the seismic S wave. This is the seismic P wave. P for primary, S for secondary. And electromagnetic waves. All the electromagnetic waves are transverse waves. Remember the electromagnetic spectrum, you should know it from the longest waves to the shortest waves, or from the shortest to the longest in the order. The longest waves are radio waves, then microwaves. So you have to know them. Now remember, all those waves are transverse waves. In transverse waves, the oscillations are perpendicular to the direction of the wave, whereas in longitudinal waves they are parallel to the direction of the wave. Okay, so I think you understand the pressure variation and the displacement of molecules. Where there are molecules close together, there is high pressure, because you have a higher concentration of molecules in the compression. Therefore the pressure is higher there compared to the rarefaction. More molecules together means there will be more collisions, which will increase the pressure. Let's go through the beginning. Alright, what is a transverse wave? A transverse wave is one where the movement of the particles or fields in an electromagnetic wave are up and down or left and right, whilst the energy travels forwards. Okay, so the oscillations will be up or down, for example, then the wave will move that way. So always the oscillations are perpendicular to the direction of the wave movement. In the case of electromagnetic waves, we have magnetic fields and electric fields which are vibrating perpendicular to each other and also perpendicular to the direction of the wave. The direction of the wave is the direction in which the energy, wave energy, is passed. This is illustrated in figure A, where the girl is vibrating the rope up and down, but the energy travels along the rope towards the boy. As the girl moves the rope up and down, the particles pull their neighbors up and down. These then pass the vibration to their neighbors through their intermolecular forces, and the wave moves along the rope. What she's doing, she's just moving the rope up and down, but the waves are moving from the girl to the boy. So the wave is going this way, but the particles in the rope are only moving up and down, up and down, up and down. So you see the rope is in place, fixed here and fixed here. The rope doesn't move from one place to another place. It's only the parts of the rope that are moving, and when they move, they transfer energy from the girl to the boy. Longitudinal wave in a fluid such as air is generated by squashing particles together and then stretching them apart from each other repeatedly, thus vibrating them longitudinally. The areas of higher pressure cause the particles to push apart from each other, but this makes the particles move and squash their neighbors, and this higher pressure, a compression, then pushes them away to squash their neighbors. Similarly, the areas where there are too fewer particles compared with the uniform spread of the particles when the wave is not present cause particles to move into the vacant space, the rarefaction, filling it up but causing a vacancy behind these particles, and the wave moves along. An example of a longitudinal wave is a solid material. In a solid material can be seen by squashing and releasing a slinky spring as shown in figure B. So if you had seen the slinky, by the way, on my channel also I have uploaded 2 videos of a slinky. One is a video in which I am creating a longitudinal wave in a slinky, and the other one is one in which a transverse wave is created, and I think there's a third one in which I created stationary wave in a slinky. Okay, so you move this backwards, forwards, then the wave is sent that way, the waves are sent that way, energy travels that way. So here you see where the coils are spread out, that is a rarefaction. Where they are closer together is a compression. So these are not fixed, it moves from here to here. So this will compress the one next to it, and then this side will be stretched. So that way the coil is moving only forward, coils are moving only forwards and backwards, but the wave energy travels to the right. A longitudinal wave generated in a slinky spring by repeatedly squashing and stretching one end. So you just move your hand forwards, backwards. Areas of higher pressure are called compressions, and areas of lower pressure are called rarefaction. See, where the coils are closer together, from the name itself you can understand that's a compression. Then the other one is where they are spaced out is called rarefaction. Graphing waves in figure A of section 5.1.1. We saw how waves can be shown on a graph of displacement versus distance. This is relatively easy with a transverse wave, as the graph appears like a picture of the wave. So it is easy to comprehend. The wavelength can be found by measuring along the graph's x-axis from one point on a wave cycle to the same point on the next wave cycle. Amplitude is measured from the x-axis vertically to a maximum displacement point. Longitudinal waves are less easy to visualize from their graph. Okay, so in the case of transverse waves, you can see the shape of the wave that we draw can correspond to the transverse wave, but we can't do that with the longitudinal wave. longitudinal waves are less easy to visualize from their graph and vice versa. Figure C illustrates how a longitudinal wave can also be represented on a graph of displacement versus distance along the wave, with the longitudinal wave corresponding wave transposed. You see here it's shown in the picture and the diagram, transposed in this way so that it has the same graphical appearance as a transverse wave. Transverse wave, you can measure its wavelength and amplitude easily from the graph in exactly the same way as for the transverse wave. Alright, okay, so here this is a longitudinal wave in a slinky. So what is happening now? The wave is going from, let's say, left to the right. Position of slinky coils in the wave. Displacement of the coils. Okay, now here you can see the coils are moving forwards, backwards. So this corresponds to center of compression. See it, center of compression. Then center of rarefaction. Then again center of compression. Here is the center of compression. At the center of the compression, the molecule or the particle, in this case the coil, has zero displacement, and even at the center of the rarefaction. So that part of the coil is neither stretched nor is neither moving forward nor backward. It's in the middle of where it is supposed to be if the coil was not disturbed, if the slinky was not disturbed. Then this point is where the coil is moved to the max, moved max to the left or moved maximum to the right. You can see here and here. So that process repeats. A longitudinal wave can be easier to measure if it is drawn on a displacement distance graph. See, displacement versus distance, how far the coil has been displaced to either the right or the left. So if it's to the right, we can say it has a positive displacement. If it's pulled to the left, it has a negative displacement. So everything on this side is pulled to the left. That's why they have negative displacements. Here to here, the coils are pushed to the right. Longitudinal waves in action. Sound waves are caused by oscillations of particles of the medium in figure D. Figure B, figure A, yeah, you see here figure D. The medium is air, causing compressions and rarefactions along the line of movement of the wave. Areas of higher pressure and lower pressure in the air continue the movement of the vibrations. An area of higher pressure, a compression, particles are close together, will occur when the particles on either side are displaced towards it, meaning particles are displaced in opposite directions towards each other to squash together and increase the pressure, as shown in figure E. See, loudspeaker produces sound by moving its cone back and forth to set up vibrations of air molecules in line with the direction of movement of the sound wave energy. The oscilloscope shows the vibrations over time. This is the cathode ray oscilloscope. This is a speaker cone. This is a microphone. So this will emit sound, this will detect the sound, and this will plot a graph of the sound behavior. Solid line pressure, dashed line displacement. So what happens where we have compressions is where we have high pressure. Where we have rarefactions, the molecules are further apart. Those are areas are where we have low pressure. Solid line pressure. Okay, so solid line, that is showing the pressure. The dashed line is showing the displacement of the particles. Sound waves are the result of areas of increased pressure moving through a body of particles by vibrating the particles back and forth. Seismic waves can vibrate the rock particles of the Earth's crust in different ways. Earthquakes are also called seismic waves. Earthquake waves are called seismic waves. They come in different types. Figure F shows primary or P waves and secondary or S waves. These are the standard longitudinal and transverse seismic waves, with P waves traveling fast and arriving first, leading to their name. Okay, so primary and secondary, these are standard longitudinal and transverse seismic waves. So you see, they are, in the case of earthquake waves or seismic waves, we have both longitudinal and transverse waves. Okay, shows primary or P waves and secondary S waves. These are the standard longitudinal and transverse seismic waves. Okay, so that's about seismic P and seismic S. S waves shakes from side to side as it travels, so you see transverse. Then P waves pushes and pulls as it travels, so it's a longitudinal wave. Both are earthquake waves. One is seismic P wave, the other one is the seismic S wave, longitudinal and transverse. Alright, that's the end of that part. Now let's go through these key definitions. Make sure you memorize them with understanding, because you may be asked to write the definitions. I think we were discussing another paper just before this theory lesson, and in that question paper you all had to answer what is a transverse wave, what is a longitudinal wave. That's why I'm telling multiple times, whatever is in these red boxes is very important. You have to memorize them with understanding, because why I say memorize, when it comes to definition, if you try to write it in your own words, you might miss certain keywords, and because of that you wouldn't get the full marks. When a definition is marked, we are looking for those keywords. Okay, so if you don't have those keywords, we can't award you all the marks for those. That's why I tell you memorize with understanding, so you don't miss any keywords. A transverse wave is one in which the oscillations occur perpendicular to the direction of movement of the wave energy. Movement of the wave is the same as the direction of movement. Direction of movement of the wave is the same as the direction of movement of the wave energy. So here the keyword is perpendicular. One of the keywords is perpendicular. So perpendicular to the direction of movement of wave energy. Longitudinal wave is one in which the oscillations occur parallel to the direction of movement of the wave energy. A compression is an area in a longitudinal wave in which the particle oscillations put them closer to each other than their equilibrium state. Okay, put them closer to each other than the equilibrium state means, now if the wave is if the particles are undisturbed, if you take for example a slinky, the coils in the slinky undisturbed, they will stay in their normal place there, but once the wave is moving, then the coils getting compressed, they are stretched, they are moved apart, just like for example you see here. So this is, let's say, undisturbed air. See, air molecules in a quiet wave. Okay, this is still a wave. Okay, here, then here they are close together. Okay, then rarefaction is an area in a longitudinal wave in which the particle oscillations put them furthest or further apart from each other than their equilibrium state. Okay, so this is the end of this lesson, and even in the diagram you can see the compressions and rarefactions. Here where the particles are closer together is where we have the compressions, where they are spaced out is where we have the rarefactions, and the definitions are important. Rarefaction is an area in a longitudinal wave in which the particle oscillations put them further apart from each other than their equilibrium state. Here they are closer to each other than their equilibrium state. Compression, rarefaction, further apart. So we have these compressions and rarefactions in longitudinal waves. Okay, so that's the end of that lesson on wave basics. So here we went through wave types. In the previous video we went through wave basics. So this was all about wave basics. Wave basics, we had two subchapters. Again, wave basics, one subchapter, the other subchapter is wave types. So here we went through transverse waves and longitudinal waves. They are very important. So again, remember the direction of the wave is the direction of the wave energy travel. Compressions are where the particles are close together. Rarefactions are where they are further apart. And this happens when there is a wave passing through the wave, where the wave is a longitudinal wave. Then remember this graph we went through. Sound wave is a longitudinal wave. You can create longitudinal waves in a slinky like this. And remember, I have also uploaded videos on my channel where I am using a slinky to create both transverse waves and longitudinal waves. One video is for longitudinal waves, the other one is for transverse waves, both in a slinky. You can watch that to have a better understanding, because when I'm creating the wave, I'm explaining it as well. Okay, then that's the end of that. Make sure you answer all these questions and check the answers as well. Make sure you answer all these questions first, the questions in the subchapters. Check your answers and then do all these questions here. Check the answers, especially these questions. Okay, so you can even skip the ones here. These are not really necessary. If you want, you can do them, but they are, yeah, you can read it. But what you have to do is these exam style questions. Do them and check the answers. And next we will see this, the behavior of waves.